Hello, and welcome to AMAT362, Probability for Statistics at UAlbany. This is lecture 23. We've only got one more lecture left after this. The theme of these two lectures is going to be an introduction to Bayesian inference, specifically focusing on this notion of the conditional distribution. We're going to start with this lecture by looking only at discrete random variables, but then make allusions as to what's going to happen in the continuous case, where we have to deal with probability density functions rather than directly with probability distributions or PMFs. Our next lecture will then look at the case of densities. This corresponds roughly to section 6 and chapter 6.1 and 2 of Pitman. All right. So let's again start with a motivating problem here. So imagine I engage in an experiment that has two natural parts. So here is our motivating question. Suppose I roll a six-sided fair die. Let's denote the outcome of this roll by x. And we know that x is distributed as a uniform random variable on the set of integers between 1 and 6. Now, once I know the value of x, say I've rolled the die once, I now flip a coin that number of times and I count the number of heads. So we're to denote the number of heads by y. So again, there's some interaction between these two random variables. X doesn't really depend on what's happened with y, but we will learn some conditional information if we know something about the outcome of y. So let's remind ourselves how this distribution works. And so let's go ahead and define it as what is the probability of a certain number of heads. I'll call this y heads, given x on the die roll. Well, again, x tells us the number of times we flip. And so I'm asking, what's the probability of y heads? Well, I need to choose y of those flips. So I need to consider x, choose y. And then I need to count the number of the probability of y heads and y tails, x minus y tails. So this looks like 1/2 to the y, and then 1/2 to the x minus y. Now I can just condense this because the base of these exponentials is the same to just be 1/2 raised to the x, which we can also think of as 2 to the minus x. Okay. Now, for ease of notation, we'll also write this as probability that capital Y equals little y conditioned on capital X equaling little x is equal to x choose y, 2 to the minus x. So this is the notion of the conditional distribution of y given x. Now, suppose I want to just figure out what's the actual PDF for y. So here we get to our real question. What is the unconditional PMF for y? All right, so we have to go back and think a little bit about how this works. Well, what we need to essentially do is figure out how y could equal a specific value, little y, by summing over all possible values x, and then considering those probabilities. So here's the answer. We need to consider the sum. I'm going to just back up a little bit. Probability that y equals a specific value, little y, is given by the sum over little x of the probability that y equals little y, given that capital X equals little x, times the probability that capital X equals little x. All right, so this is sometimes called the law of total probability. Or sometimes people call it the rule of averaged conditionals. All right, this is the one that Pittman likes to use, but plenty of other books, including the MIT book, Bertzmes and Tsitsiklis, like to use this term. If you look it up, you'll find, I think, either one. All right, now let's apply this formula to the specific case of the problem at hand. All right, so we know that, oops. That x is uniform on the set of integers between 1 and 6. So that means that when we look at the probability of y equals little y, and we know that this is the sum over possible values of x, probability of y equals little y, given that capital X equals little x, times the probability that capital X equals little x, we now know that this guy right here is equal to 1/6, as long as x is between 1 and 6. And we have a formula for this as well. We know that this is little x choose little y, 2 to the minus x. So now we just need to multiply these things together and sum accordingly. So what this is going to look like is 1/6 times the sum from, let's say, little x equals 1 to 6 of x choose y, 1 over 2 to the x. Let's try to understand this formula for maybe a specific value. So what's the probability that we get 0 heads? Well, we could have rolled the die, got a 1, and then for our 1 toss of the coin, got a tails. So we had no heads. This would say that, well, 1/6 is the probability of rolling a 1. Oops, sorry, probably that x equals 1. Times the probability of getting a single tails, which is just 1/2. Probability that of no heads, given that x equals 1. Similarly, could have rolled a 2, and now I need to require that both my flips were tails. So that's a probability of 1/2 squared. If you can start to see the pattern, could have also rolled a 3, and then I would have had to require that I get a tails 3 times. That's probability of 1/2 to the 3rd. And then I sum up the next 2 and finally I get 1/6 times 1/2 to the 6th. So if you work this out, you'll end up getting something like, well, 6 factors out, so you just need to figure out this partial geometric series. And you'll see that it ends up equaling 63 divided by 64 times the sixth. So that's the probability that y equals 0. All right, apologies for the pause. I want to go ahead and then show you how to think about both the distributions involved here and really what this process is going through. So let's turn to Pitman really quickly. So you can see here, we've got the conditional distribution for the number of heads out of X throws, given that we know the value of X. Now, if I say I know I rolled a 1 on the die, then there are only two possibilities and they have each equal probability. But if I rolled, let's say, a 2, then I've got 3 possibilities. And what I'm looking at here is just the binomial distribution, where I'm changing the value of n, where n is now X. That's the value of our die roll. And so you can see how this ends up being sort of averaged out. Now, what we're going through when we're trying to compute, let's say, the probability of getting a certain number of heads where we don't know the value of X, we need to accumulate for all the possible ways that X could be. So in particular, if you run through the calculation here, we end up getting this value. And I'm just going to go ahead and bring this into our notebook over here. So now I can say something about what's happening in general. I now have this distribution, and you can see that these numbers don't look particularly appealing, because in particular, I've had to consider all possible values of X and then figured out what the binomial value is for each of these. In the case for y equals 0, it's pretty straightforward because we're assuming we have to flip tails all the time. So that means the binomial coefficient's 1. And then I'm just focusing on what is 2 raised to the negative number of rolls. And so that's where we had 1/2 versus when X equals 1, 1/2 squared when X equals 2, 1/2 cubed when X equals 3, and so on. So let's go ahead and consider what is going on here and what is it that we just did here. So just to give you some terminology, what we've been looking at back here is the conditional distribution. For y given X. And the process that we just applied to compute the probability distribution for y, the unconditional probability distribution for y, was essentially an expression of what I'll call marginalization, or what we called marginalization, when we knew what the joint Pmf was. So let me go ahead and just remark here that this is essentially marginalization of the joint Pmf for probability that X equals little x, Y equals little y. Now, again, luckily, Pitman has actually worked out this joint distribution for us. And it's right here. So let me go ahead and just grab this and explain how these numbers came about. Oops. All right, so now this is the joint PMF for probability that die roll, let's call that X, is equal to little x, and number of heads which we call y is equal to little y over all possible values of little y and little x. And you'll see here that when we take this joint PMF and we sum along all the values for y, we actually regain the uniform distribution on 1 through 6, which is the probability of getting a given heads. Now, what we just computed the very first entry of, in which the table was last time, this was essentially the probability that y equals 0. And you'll see that we essentially had this calculation of, all right, probability that x equals 1, and then what was the probability that y equals 1, or y equals 0 in this case, given that x equals 1. And so by considering that joint probability for each of these possible values, we obtained this collection of numbers that when we sum up, we end up getting this number here on the right. And so you end up seeing this sort of distribution that looks fairly complicated. But again, this is essentially an expression of marginalization. But the fact that one of the terms involved here, namely this one, the one that tells me what's the probability of y given the value of x, makes things look slightly differently. So let me just go ahead and write this down again. So the rule of averaged conditionals essentially says this, which is that probability that capital Y equals little y is equal to the sum over all possible values of x of probability that y equals little y, given that capital X equals little x, times the probability that capital X equals little x. Now, remember the way conditional probability is defined, it's just an and statement rather than divided by the probability. So if I go ahead and write that out, this is the same thing as saying that the probability, asking the probability that y equals y and x equals little x divided by the probability that x equals little x. But if we go ahead and cancel this out, we now see that this is essentially just the expression of marginalization. So this process right here is just the same thing as the rule for marginalization. And it's called the rule for marginalization because like once you have this joint probability table, you can write in the margins what the probabilities for either X or Y is just by summing up either rows or columns. When we're, in this case, doing Y, we're summing along the rows, and we're trying to find the probability for X, we're summing along the columns. And then we can write in the margins what's the probability distribution for each of these. All right, great. Now, let's go ahead and leverage this into one of our first instances or a reminder of how Bayes' rule, because sometimes we'll be in situations where even though a process is sort of naturally a two-step thing, here we're rolling a die and then we're flipping a number of coins, sometimes we're only informed about what the output of the final step is. Let's say I got 3 heads, or let's say I got 2 heads, but you're not told how many times you flipped the coin. But nevertheless, knowing that I got 2 heads allows me to sort of narrow the set of possibilities and also get more information on what was the value of the roll, which determined the number of times I flipped the coin. So let's go ahead and see how that works in this case. So we also have a setting here of, let's go look at this example of Bayes' rule. So suppose we're told the result of this two-step experiment, i.e., we are told the value of Y, but we don't know the value of X. How can we use the information about Y to inform us about what happened in the first stage of this experiment? And again, you should kind of think about it. We had here X equals roll a die. Make this a little shorter. And then that informed Y, which was flip X coins. And then we eventually just reported count the number of heads. And this was the value or the output of Y. We're kind of curious about how can we go back and do this inference process. So just as a reminder, here we have to use essentially Bayes' rule. So the question is, let's find the probability that capital X equals little x, given the information that capital Y equaled little y. So this was, again, the value of the roll. And this over here was the number of heads observed. Well, by Bayes' rule, we can say the following, which is probability that capital X equals little x, given that capital Y equals little y. It's the same thing. We could just write the definition, but let's go ahead and jump to what the final form is, which is the probability that Y equals little y, given that X was equal to little x. but we have to multiply by the probability that x was equal to little x. And then we divide by the probability that y equals little y. So remember, this is another expression of Bayes' rule. Now, what does this look like in this case? And let's be a little more specific. Let's figure out what happens. We know that y is equal to 2. Well, there are a couple things which are sort of easy, right? We know what the probability that x is any given value when we don't have any information. It's as long as that value is 1 through 6, we know that the probability is 1 out of 6 because it was uniform. And that's how we actually then compute the probability that y was actually equal to 2, given whatever that value was. So we can go ahead and try to fill out this table. And let's go ahead and do this. So what's the probability that x equaled 1, given the information that y was equal to 2? Now let's think about this. We're told that we had 2 heads, but the rule of the experiment was, given the value of x, we're going to flip the number of coins, or the coin a number of times, equal to whatever x was. Well, we know we got 2 heads. So that means we had to at least flip this coin twice, which actually says that this is impossible. So the probability of this is 0. It's the same thing as saying impossible. It's just probability 0. Because had 2 heads. And that automatically implies that x has to be greater than or equal to 2. In particular, the probability that x equals 1 is 0. Okay, so now let's do something a little more interesting. Let's look at the first non-trivial case. So what's the probability that x equals 2, given that y equals 2? Now, this doesn't necessarily feel as likely, but it is possible. Let's figure out exactly what the probability is. Well, the value upstairs has to be, all right, well, it's the binomial formula, but we're with x equals 2. So it's 2 choose 2. And then we have 1/2 squared. We got 2 heads times the probability of getting a 2, which was a 6th. And then I need to divide this by all the ways in which y could equal 2. Well, what that amounts to doing is computing the sum from x equals 2 to 6 of x choose 2. I got 2 heads, so that means 1/2 squared. And then I got the remaining x minus 2 tails. And this is all multiplied by the probability of a 6th. This here is, again, just the law of total probability being applied. Now, luckily, we know what this is. This is equal to the probability that y equals 2. And what this is given by is, if I turn back, I'm summing this row. And so we can see that 99 out of 384 was the value here. So we can then plug all of this in, and we can get now the conditional probability for x given the information about y. Now that's not easy to read off from our table, but we now know that it's actually equal to 16 over 99. Once we plug all this in here, we end up getting, a 4th times the 6th, and then we already know that that is going to give me a 24th. So then I end up having to divide 24 into 384, and I think that works out to be something like 16. All right, so this is already now a pretty complicated distribution, and you'd have to go through and compute that for every possible value. let's go ahead and just now look at what this conditional distribution is. So now we can actually get at it a little bit here. So we can say, again, from repeating this calculation for x equals 3, 4, 5, and 6, all conditioned on y equals 2. We then get this table. Now, let's take a moment to think a little bit about this, because one of the methods which ends up coming out of statistics is that you should choose your parameters, or choose your value of x in a way that maximizes the likelihood of what you just observed. So this kind of leads into an aside. So I'll just call this a sort of statistical aside. So there's a principle called of maximum likelihood, which is sometimes called a maximal likelihood estimator. Or MLE, is essentially the principle that if you've observed some data, namely that you got 2 heads after you produce this process, you choose the parameters for x that makes that data most likely. In this case, we actually have things are sort of split between x equals 3 and x equals 4, because in both cases, the probability was maximized for those 2 values. So in other words, is the most likely explanation for the data. You kind of almost can think of this as like an Occam's razor of some sort. Which can be interpreted in various ways, but one way of saying it is it's the, you should always choose the explanation, the simplest explanation that explains the observation. And that simplest explanation tends to be the one that's right. So it's a slight variation on that. Anyhow, there are other ways in which we can sort of choose. Now, again, in this case, what we're doing is we're choosing the mode. Right, so most likely, in some sense, is also the mode, which we did a lecture on. What are the ways in which we can interpret the mode, the median, and the mean? And it turns out that if you have different sort of guessing strategies and you have different penalty functions, each one of these leads to a better or worse penalty depending on whether you're right or not. In the case of the mode, I think this is the one where the penalty was just either win or you don't win. And if you either win or you don't win, and there's no, reward for being close to the answer, then you should always just pick the most likely thing, i.e. you should pick the mode. Let's take a moment to consider what's the mean of this distribution, because that optimizes a slightly different problem. So let's consider the situation of reward schemes. i.e. The median and mean. And so this gets into the question of how could we, let's say, compute the expected value for the number of heads. And then we can even turn this on its head, no pun intended, to then figure out what would be the sort of expected value for y conditioned on certain information. Right. So just to finish this thought, for example, so for this example, instead of guessing x equals 3 or 4, given that y equals 2, you could try to do some sort of long-range estimate. You could look at the expected value of x conditioned on y equals 2. And this would just amount to averaging these values out across 1 out of 6. So this would just end up being whatever x is times the probability that x equals little x given that y equals 2. So this could be another choice. All right, so let's go ahead and maybe back up a bit and then look again at expectations in the setting of conditional distributions. And let's not attack this one directly because we can already see the numbers are kind of complicated. I could just do the algebra. There's not really much to learn here, aside from getting a number out that could be useful. Let's look at another way of turning around this problem. So let's consider another instance. So now expectation of conditional distributions. And we can even just think of this as conditional random variables, as I'll try to explain now. So again, here's a motivating question. So suppose we know that, all right, we want to know the expected value of y. But you can see this is hard to compute because the way that we figured out, well, what was the probability that y equals little y? Well, we went over to this table and had to figure out, okay, this sum equals this. So that would be the probability of y, and then I'd take that times 0 to get the expected value of y. So I could basically take this column here, multiply by 0, 1, 2, 3, 4, 5, and 6, and then get a value out, and that would be the expected value for y. Now, I'm going to show you another way of doing this that's actually a lot faster and simpler. And it uses something called the Law of Iterated Expectations. So, but we know this is conditioned on x. So let's start by just trying to figure out what is the expectation of y given x. Now, again, by definition, we can just say that, well, we know that this is the sum over all possible values y of y times the probability that y is equal to little y given that x equals little x. So that's the definition of this. But we're going to go ahead and see that in this case, things are relatively simple because we can interpret y, given that we know the value of x, as simply a binomial. So remember, this right here is a binomial random variable with n equals little x and p equal to 1/2. So in particular, this ends up equaling n times p, but let's go ahead and be more precise and let's plug in, well, we know that n is equal to x and p is equal to 1/2. Now this is actually really nice because we can now go ahead and move through and compute what is the expectation for y, now that we've used this conditional expectation. So the expectation of y can now be identified as the sum over the expectation of y given that x equals little x times the probability that x equals little x. Because this really is just a function of the random variable x. And remember, whenever we want to compute, let's say, the expectation of g of x, by definition, this is just the sum of g of little x times the probability that capital X equals little x. So this formula works. The one I just wrote down is correct. And intuitively, this also makes sense because we know the expected value for y, assuming we know x, and it ends up being x over 2. So now we just need to sum up over the possible values of x and their probabilities. So this ends up equaling the probability that this ends up equaling sum from x equals 1 to 6 of x divided by 2 times 1/6. Now notice this actually looks almost identical to the expectation for x, except I have this extra factor of 2 here. So let me just go ahead and pull that out. So there's 1/2 times the sum of x equals 1 to 6 of x times the probability that x equals little x. And this ends up equaling the expectation of x, which we know for a dice roll is something like 7/2, which is 3.5. And so I just now have 7/4 as the answer for the expectation of y. And which ends up equaling something like a 1.75. So the expectation of y equals the expectation of x divided by 2, which equals 1.75. Now let me go ahead and step back and sort of formalize or give you a compressed way of writing this expression right here. So this is just the definition of the expectation of a function of x, but there's a really slick way of writing this, especially when we're dealing with conditional random variables. And this is what's called the law of iterated expectations. And it says this, it says that the expectation of y given x is just equal to the expectation of y. Now, this can be a little perplexing, but you need to think about how this is actually defined. So to think about it, this is an expression. The thing inside this outer square brackets, we think of this as a number that is dependent on the value little x of x. And we know that the value little x of x has a probability. And so then to compute this sort of expected value of this expression, this function, g of x, it's a function, g of x, we just need to sum over all the probabilities of, we need to take each of those values, the expectation of y, given that x equals little x, and then multiply that by the probability that x equals little x, and now sum over all the little x's. And this ends up being exactly the expression for the expectation of y. So this is a very useful tool, especially when y is, in some sense, defined conditioned on x. For a quick proof of it, we know why this works, right? So here's a quick proof. So we know that the expectation of y can be viewed as the sum, or actually let me start with the left-hand side. So we know that the expectation of y given x is equal to, well, it's the sum over all possible values little x of the expectation of y given that x equals little x times the probability that x equals little x. Now let's remember, how is this inner expectation defined? Well, I need to sum over all the possible values for y, where I take y times the probability that y equals little y, given that x equals little x. And again, I'm now taking this expression times the probability that x equals little x. Now, again, we can think of this as, we can think of the definition of this in terms of an and, which looks something like this. We have y, probability that, let's say x equals little x, y equals little y, divided by the probability that x equals little x, times the probability that x equals little x. And then, we see these factors go away. And so if I sort of repurpose some of this summation, if I reorder the sum, the sigmas, this ends up looking like sum over y, sum over x of, let's say, if I fix y out here, then this just looks like the probability that x equals x fixed for y. But then this ends up giving me the value of the probability distribution for y, just by marginalization. That's this step right here. This marginalizes and so finally we recognize this expression here. This is exactly the expectation of y. And that's the end of the proof. So these two things do actually cohere and they make sense. Now let me go ahead and flip this around as I was intending to. And maybe we should look at a situation where we can turn this result on its head. So let's turn this result on its head. And let's suppose we want to know something like what is the expected value for x, given that we know certain values of y. Well, if we condition, then this is just collapses to the usual formula. So remember, we want to compute the expectation of x given that we know the value of y equals 2. Well, by definition, we need to sum over the probability, or x times the probability that x equals little x, given that y equals 2. And so, and this is defined in this sort of long, complicated way. But we can do better if we allow the output of y to actually vary. So this doesn't answer the direct question, it answers a slightly different question. And let's go ahead and just sort of test our understanding of what just happened. Okay, so what is the expectation of x given y? That's a function of y, but now I'm going to take the expectation of this, viewed as a function of y. So this is a function of y. Well, by the law of iterated expectations, this actually ends up being the same thing as the expected value of x, which we already know is 7/2. And that's what I meant when I said, let's turn this result on its head. We have this. So recall this simpler problem. But it's actually hard to calculate. can instead answer this more general question just by using this law of iterated expectations. So I want to take a final moment here to just reflect on what's going on. I'm going to introduce some slightly different notation to hopefully inspire you, or at least make any notation you see in a future statistics class a little less scary. All right, so what is going on here? So previously, we knew that because this was a two-step process where the second step was conditioned on the first, we could compute probabilities that were sort of implicitly conditional, even though it's not a thing we technically defined before. And so here we're looking at what's the probability that y equals a certain number of heads, assuming we know the number of times we're going to be flipping our coin, and we know the probability of a heads here, right? And so in this case, it reduced to our old friend, which is the binomial distribution. Capital N, choose little n sub h times p to the little n sub h times q to the capital N minus little n sub h. This is our usual binomial formula. But what we also considered was what happens when we sort of flip things around. And let's say we know that the number of heads was 2, and we want to now get information about what was capital N. This is also what we call little x. So basically now let's fix n sub h to equal 2. Again, we know that p equals a half. We're going to let x vary. And so we now get something that's a little different. So the probability that capital X equals, let's say, some value little x, we don't know, given that n sub h equals 2, p is equal to half, is going to look like, well, I need to take my binomial expression, but now plug in little x for capital N, n sub h, which we know is 2. All right, x choose 2. P squared q to the x minus 2. And then, of course, this was multiplied by a 6th by using Bayes' rule. This was just the probability that capital X equals little x, but not the conditional probability. And that's what we're finding here in this fraction. And then we summed over x equals 2 to 6. X choose 2. P half q to the x minus 2. Again, times a 6th. And what's happening here is we're essentially computing total probability of NH equals 2. Because just like in any conditional probability, we have to, at the end of the day, divide by the probability of our events. Right now, we're ignoring the fact that we know that this coin is a fair coin. Now, this expression can actually be sort of written out in English as follows. And this is really called I would say, the fundamental paradigm for Bayesian statistics. Stats. And it says essentially this, that the posterior is equal to the likelihood multiplied by the prior divided by probability of the evidence. So you should think of this as probability so I'll think of this posterior probability and I want to think of this as the probability of the evidence. And this is over here is the prior probability. And essentially what happened here is that the prior probability was the prior probability of any of our rolls, the value of the die. And we saw that we started with an assumption that any value is equally likely, meaning we had a 1/6 chance of any given value for the die roll. But when I then multiplied that 1/6 times the likelihood, so this was essentially the probability that X equals a particular value, times that prior, and then I divided by the total probability of the observed outcome, which in this case was, I got 2 heads, probability of my evidence. By letting X vary, I now get a posterior probability distribution. And we'll see that this actually now, as we saw over here, kind of has a hump. So it starts off as 0, goes up some more, it peaks down, it comes down a little bit, and then it comes down a little more before dropping to 0. So this ends up being our posterior probability distribution. So this ends up being our posterior probability. And it's the new distribution we should put on the value for our dice roll, given that we have extra information. All right, so I apologize if this lecture seemed a little scattered, but I think there are a lot of important ideas. And then in the next lecture, we'll pick this up and then look at continuous random variables. And we'll look at the all important case of how do you know if your coin's fair or not? If you flip it a certain number of times and you get a certain number of heads, how does that inform your belief about the coin? All right. Look forward to seeing you in class soon.